So here is another multi-step synthesis problem involving carbonyls, and as you can see in this question, you are to start with this ketoester and convert it to this acetal and thioacetal in 4 steps. So go ahead and pause and restart when you are ready. So as you can see, you are converting this ketone here to an acetal, and then here you're converting this ester into a thioacetal, and you should do this in 4 steps. So the first step is going to be converting this ketone to the acetal, and then what you would do is reduce the ester to an aldehyde or to an alcohol and to an aldehyde. If you don't know the reducing agent that will stop at the aldehyde stage. By this time I have taught this chapter, we did not talk about the partial reduction to an aldehyde without going all the way to an alcohol. So you can first convert this to an alcohol and then convert that to an aldehyde and then convert that to the thioester. You do not want to reduce this right away, because if you use something like lithium aluminum hydride to reduce the ester to an alcohol, then you are going to also reduce the ketone, which will prevent you from converting this ketone to a acetal here. Therefore, the first step is going to be converting the ketone to the acetal using ethylene glycol and acid. So you're going to say H plus catalytic amount of acid and ethylene glycol and minus H2O to show that this could be a reaction that could be done in a one-sided manner without reversibility, and that is going to keep your ester intact. And as you know, esters are less reactive towards a nucleophile compared to a ketone is because of the lone pair conjugating, right? Because the lone pair conjugates, that reduces the electrophilicity of this carbon. So therefore the ester is going to be unreactive towards, or less reactive towards, the nucleophile, which is ethylene glycol, compared to the ketones. Therefore you are going to convert your ketone to the acetal, okay, and this could be considered as the R group. This whole chain, I'm just going to designate it as R. So now we protected your ketone. Now if you reduce your ketone, if you reduce the molecule with lithium aluminum hydride, then it is going to reduce the ester to an alcohol, to a primary alcohol. So that is still the acetal. The acetal is going to be unreactive towards lithium aluminum hydride once it converts to this structure, right, which is acetal. So acetal is not going to be reduced or affected by lithium aluminum hydride. You won't treat this with water, just reduce it with lithium aluminum hydride. That will convert your ester to an primary alcohol, and the other part of the molecule again is going to be the same. Now what you want to do is use PCC to oxidize your alcohol, primary alcohol, to an aldehyde without going all the way to the carboxylic acid. So we have an aldehyde, and again this acetal is unaffected. And now if you treat this with the specific alcohol, which is 1,2,3-propane 1,3-dithiol, right? So 1, 2, 3 SH, right? So 1, 2, 3 sulfurs, and that carbon here is going to be that carbon. So if you use catalytic amount of acid again and remove water to make it a one-sided reaction with the propane 1,3-dithiol, you will get this aldehyde group converted to the thioacetal. So this is the overall scheme. So step 1, step 2, step 3, and step 4. So again, there is, once you come to carboxylic acid and their derivatives, you will know a way to convert your ester, reduce your ester to an aldehyde without reducing it all the way to an alcohol, but that is in chapter 20 in the organic chemistry second semester, and therefore you don't have to worry about that reaction now. But once you come to chapter 20, you will know a way to reduce your ester directly to an aldehyde without going all the way to an alcohol. But right now we don't know that, therefore we are using lithium aluminum hydride, which will reduce your ester to the primary alcohol.